Okay, this is chapter 9. The first half of chapter 9 is one sample proportions for population proportions. The second half of chapter 9 will be population means, essentially. In both cases, we're doing hypothesis testing. So all of chapters 8 and 9 are a topic called inference. We're inferring as to what we believe the true answer to be. So we used confidence intervals in chapter 8 to infer as to where we believe the true answer to fall. And now we're going to do hypothesis testing to test hypotheses, essentially, infer whether we believe they are true or not, or if some alternative hypothesis may be true. So let me get my little tool here. Maybe go tools. Okay. So in hypothesis testing, you have two types of hypotheses. You have the null hypothesis, or your default belief, and you have the alternative hypothesis, or what you're researching, or what you alternatively believe. So they either use 0 or n in most books for null hypothesis. We're going to use 0. Most books use either 1 or a for the alternative hypothesis. We're going to use the a for our alternative hypothesis. So essentially, whatever the null is, the alternative must be the opposite. So if the null is equal, then it must be greater than, less than, or not equal to. Okay, sometimes they'll write it like this, which means not equal, right? The exclamation means not. So it depends. So typically it's going to be one or the other. This is the more common one in math. This one's the more common in computer science. If the null hypothesis is greater than or equal to, then this one must be less than for the alternative, right? Less than. And if it's less than or equal to, then this must be greater than, right? It's the alternative argument, essentially. Okay? All right, so let me copy this. Copy. And paste. Okay. What you notice is in every one of these cases, the null hypothesis has an equal in it, right? There's an equal in it. There's an equal in it. There's an equal in it, correct? Typically in Stats 1, you don't need to worry about the greater than or less than part for the null hypothesis. You can just always put equal for the null hypothesis. It won't really matter for the calculations or the outcome. The null hypothesis never has an equal in it, right? Notice there's no equal, there's no equal, there's no equal, right? There's no equal ever in the null alternative hypothesis. Okay, so long story short, the null hypothesis always has an equal in it. The alternative hypothesis never has an equal in it. Okay, you do not need to do these versions in Stats 1. You can if you want, but you don't need to. You can just write it always as equal for the null hypothesis, which is what I'll do. Okay, so this is the common wording you should look for. And there's only 3 types of tests, which are the same mathematics we did in the past using Z. You can have a left-tailed test. You can have a right-tailed test. Or a two-tailed test where you account for both of them, essentially. Okay, so it's a left-tailed test if the alternative is to the left, right? So this is the left tail, alternatives to the left. Right tail is to the right. And not equal to just means account for both of them, essentially. Okay, and we'll calculate those values. So essentially, we want to know, should we accept the null hypothesis, or did we prove the alternative hypothesis, right? So we essentially have to look at our data to prove or insinuate truth about one or the other. We don't know without doing some calculations. So there's basically 4 steps to it. We're going to use Z when it's proportions, basically. Identify the parameters, name the test, and write the hypotheses, right? Check the conditions to see if the sampling distribution can be done, and then describe the sampling distribution. Okay. Collect random samples of the population, right? Do the tests, and make conclusions. Those are the 4 steps, essentially. All right, so we need a Z statistic for this. So the Z statistic is very similar to Z in the past. It's the sample minus the population, and then we have the standard error on the bottom, basically. A lot of times we'll just write this as SE, right? So our standard error or the standard deviation of the sampling distribution is p times q divided by n, all square root essentially. Okay? All right, and then the mean of the sample proportions, the mean of the population should match essentially. Okay, so when we do the hypothesis testing, we have to look at the p-value and the significance level, which is alpha. It's a similar or same alpha as the confidence intervals we did before. They are related. We'll talk about that at some other point. Okay. If p is low, the null must go. So if the p-value is less than alpha, you reject it, which means we have enough evidence to suggest the alternative hypothesis is true. If p is not low, which means it's more than alpha, do not reject the null hypothesis. There's not enough evidence to say that the alternative hypothesis is true. Yes, it can also be equal to, but the probability of that happening is so low, you might as well just ignore it essentially. Okay, and again, the things we have to check is n times p and n times q are greater than or equal to 10. Okay, that'll satisfy our normality basically, which is what we want to do in step 2 of the hypothesis test. Okay, so before we do hypothesis testing for those 4 steps, we want to look at a couple things here. So if the hypotheses are these, then the mean here is 10, and we want to do a left-tailed test essentially, right? So that's our p-value in there essentially is our p-value. Okay, so we're doing a left test. Okay, left-tailed test. Okay, if it's a proportion one, right? So the last one was mean is proportion, then this is 0.2. And we believe, alternatively, it's more than that. So we have a p-value over here, essentially, as to what that area is, right? It's in here. So when I say p-value, what I'm really saying is probability value or proportion value, which is area, right? Area is probability or proportion in statistics for us, right? Let's say we have a not equal to one. So we say we believe it's 0.56 is the true population, right? And then a two-tailed test would be not equal to, so it means it could be less than or greater than. So we have this area and we have this area. This area is half of the p-value. And this area over here is the other half of the p-value. So when a two-tailed test, when it's a not equal to, okay, it's area on both sides essentially. So both of those together is the p-value. Okay, so do one more. Do we have one more? Yeah, so it's a mean, right? And let's see, we believe this is 37. Okay. Come on, don't quit on me here. Please don't quit. Thank you. 37. And this is a greater than, right? So the p-value is over here somewhere. Okay, so essentially this is mu, or mean 37. The previous one was proportion. So we believe it's 37. At 37 what? I have no idea. This could be punches to the face, number of cars you own. Who knows what this 37 is? What the problem is about? So we need to find enough evidence. So if we get into this area over here, okay, then we found enough evidence essentially. So this is our p-value over here, which is this shaded area. Okay, so this can work for proportion, mean, or anything else we want to prove essentially, or disprove. Okay, so the claim, what we're claiming can be either one. We can either claim the null hypothesis or the alternative hypothesis. It doesn't matter. Okay, the point is if p is low, the null must go. Okay, so here, what you have here, let's say I did the hypothesis test and I calculated a p-value of this. Okay, and my alpha is this. Okay, well this is lower than this, isn't it? That's about 2.3%, that's about 5%. So that means the null hypothesis must go. Whoops, let me get rid of this. So that means there is significant evidence to reject the null hypothesis. There's enough evidence to suggest the alternative hypothesis is true. Because you must accept this unless you find evidence. We are rejecting it because we found enough evidence, because the p-value is low, essentially. Okay? Versus here, this p-value is higher than this, which means we cannot reject the null hypothesis. There's not enough evidence to suggest this is true, right? This means not enough evidence, essentially. So, very similar statement. There is not enough evidence to reject the null hypothesis. There is not enough evidence to suggest the alternative hypothesis is true. So essentially, you assume the null hypothesis unless otherwise proven to the alternative, essentially. Okay? And you're finding evidence by doing calculations. That calculation is a p-value, which we're going to go over in the next value as to how you get that p-value, essentially. Okay, so that's the same for mean, proportion, or anything else you're doing a hypothesis test for. Okay? So, does that change for a two-tailed test? No, it doesn't. Okay, so here the p-value is more than the alpha, right? So therefore, there's not enough evidence. Okay, so does it matter that you are personally claiming the null hypothesis or you're personally claiming the alternative hypothesis is what you believe? No, it does not. Whatever you're claiming to be true does not matter. It's a matter of comparing these two things, and you either reject the null hypothesis or you don't. So here, this is bigger, so therefore I do not reject the null hypothesis, so therefore there's not enough evidence for this one, so I have to accept this, essentially. Versus, again, this one I'm claiming the alternative, which doesn't really matter which one I claim. Okay, what is important is this p-value that I calculated is lower than the alpha, which means I need to reject the null hypothesis and accept the alternative hypothesis because I found enough evidence, essentially. It's irrelevant the fact that it's the claim. Whatever you're claiming to be true or you want to be true does not really matter, essentially. So you can ignore the general idea of claim in Stats 1, essentially. Okay. Okay, so in the next section we'll do some actual hypothesis testing and we'll calculate the p-value and actually make some conclusions.